Hello, my name is Matthew Du. I'm part of the Yuen-Zhou group at UCSD. Today, I will share our work on remote control of chemistry and optical cavities. First, let's discuss strong light matter coupling, which happens to molecules inside optical cavities. If you shine a laser at a molecule outside of a microcavity, you will excite the molecule, and then after some time, the energy will be dissipated either radiatively or non-radiatively. Consider what happens for a molecule inside a microcavity. A microcavity is the space between two mirrors, which are highly reflective, such that a photon between them will bounce back and forth many times and therefore be trapped. So, if you shine light on the light layer system, what you'll see is that a cavity photon will be excited, and then the excitation will oscillate between cavity and photon several times before finally escaping the cavity. This phenomenon manifests in its peak splitting in the optical spectrum. For the molecule outside of cavity, if you have a single peak corresponding to some molecular transition, then inside the cavity, the transmission spectrum will contain two peaks, one above the molecular transition energy and one below the molecular transition energy. This can be understood in the following diagram. So a photon strongly couples to a collective molecular mode of matching symmetry to form upper polariton and lower polariton. In a molecular sample, there are a macroscopic number of molecules. So the vast majority of molecules states will remain uncoupled to light and form the dark states. Right? So even though they don't couple to light, these states are very important because there are many of them, right, compared to the polariton states. So they will affect the relaxation dynamics of the polariton states. Right, so due to the new energy levels formed, right, whose splitting scales with concentration, as well as the new density of states, this shows that strong light matter coupling has great potential to modify and control chemical reactivity. Indeed, it was found that for an organic reaction, substitution reaction carried out in the microcavity, not only is the reaction found to be suppressed, but as they change the concentration, they change the rate constant. A similar reaction, but one with two possible products, was explored in a microcavity, and it was found that depending on whether they tuned the cavity to be resonant with one of the vibrational modes, or if they made the cavity off resonant with any of those modes, they could change the product selectivity. This remarkable tuning of chemical reactivity has also been shown for photoisomerization reactions. Another photochemical process that is modified under strong light matter coupling is energy transfer. For a donor and acceptor chromophore inside a microcavity, it was found that as they increase the distance between donor and acceptor to hundreds of nanometers, not only did they see energy transfer, but they saw that it was distance independent. To explain this remarkable finding, there were subsequent theoretical works which propose a mechanism consistent with this observation, namely the energy transfer in the strong light matter coupling regime occurs via transitions between polariton to dark states and then dark state to polariton states. The transition from polariton to dark states is relatively fast due to the high density of dark states, and the transition from dark states to polariton states is relatively slow, but still fast enough to observe experimentally. and both of these transitions occur via vibrational relaxation. Inspired by the ability for strong light matter coupling to modify chemical reactivity, as well as enable a chemical process between molecules that are separated by hundreds of nanometers, we decided to develop a remote control of chemistry. This device consists of two optical cavities, which have a common mirror, where one microcavity contains a remote catalyst, here glycolic acid, and the other contains the reactant cis-HONO. Both molecules have an OH stretch mode that are strongly coupled to the photon in their host cavity. With this configuration, we show that by photoexciting the remote catalyst, we can enhance the cis-to-trans isomerization of HONO. Let's see how this works. Consider the remote control device in the off configuration. So for each side of the polaritonic device, we have the polaritonic states, right, formed by each cavity and the molecules strongly coupled that live within, right? In this device, the middle mirror is thin enough such that a photon can tunnel between cavities. Thus, the cavities are coupled and the polariton states are delocalized across both cavity modes, remote catalyst, and reactant. All the species within the device. Now, in the off configuration, the propulse is chosen to be off resonant with the lowest polariton, such that the lowest polariton does not absorb efficiently and there's inefficient reaction. Let's consider before we consider the on configuration where we pump the remote catalyst, let's try to understand what happens when vibrational polaritons are pumped and then probed with the subsequent pulse. So, if the upper polariton is pumped, what happens is that due to the high density of dark states within 1 to 10 picoseconds, the excitation will relax into the dark states. Now, because molecular vibrations are inharmonic, the next transition of this excited state population, the 1 to 2 transition, will be smaller in energy compared to the 0 to 1 transition, and therefore cavity energy. Thus, exciting the strongly coupled vibrational mode will effectively reduce the light matter coupling. This results in a reduction in peak splitting, which can be detected with subsequent propulse. Indeed, this has been shown experimentally, where if you look at the black curve, which has no pumping, and then compare it to the red or blue, which have higher and higher pumping intensity, the splitting between polariton peaks decreases. Let's return to the remote control device. In this case, we have the energy levels as shown in the previous slide. And then if you pump the upper polariton, because it has most of the character of the remote catalyst in its cavity, it will relax very quickly into the remote catalyst dark states, which then change energy levels such that the lowest polariton state is not only resonant with the propulse, it now has more reactive character. These changes lead to this lowest polariton efficiently coupling into the product state. Let's look at some calculations. Calculations shown in the next slides have been computed with input-output theory. We won't go into too much detail, but basically input-output theory allows you to take the equations of motions, right, for your cavity and molecular modes, where input-output relations which relate the input excitation to output degrees of freedom, and these allow you to calculate observables, including reflection, transmission, absorption, and reaction efficiency. Satisfyingly, This formalism yields an effective Hamiltonian, which demonstrates the reduction in the light matter coupling between remote catalyst and its cavity as you increase the fraction of the molecular species that is pumped. Looking at the absorption spectra, you see that as you change the fraction of remote catalyst pump, you change the peak positions. If we now focus on this frequency region, we see that the corresponding reaction efficiency, the corresponding efficiency for the reaction induced by the probe pulse, closely follows the absorption. This makes sense because the more energy that goes into the reactant, the more energy there's more energy that will go into the reaction coordinate. Right? So if we now focus on the pink line, at this frequency, we find that as we increase the pump intensity for the remote catalyst, we can increase the reaction efficiency by an order of magnitude. Therefore, we've demonstrated remote control of chemistry. Even if you don't have all the fancy nonlinear spectra equipment, though, you can still do remote control of chemistry by either changing the thickness of the metal mirror or increasing the concentration of the remote catalyst. With zero pumping, as shown by this cross section here, you can still change the reaction efficiency by an order of magnitude. In summary, we've shown that with the proposed polaritonic device, you can do something to one molecule and change the reactivity of another molecule, even though the molecules live in separate vessels. Similarly, you can change the reaction efficiency by modifying the thickness of the middle mirror or changing the concentration of the remote catalyst. Future directions include extending this remote control technique to photochemical reactions in excited electronic states, such as photoexcitation and spin conversion, both of which have already begun to be explored in the strong light matter coupling regime. I'd like to thank Professor Yuen-Zhou, my advisor, and Dr. Raphael Ribeiro, my postdoc mentor, as well as all these funding sources. Thank you for your attention.